Yeah, good morning, children. See, first of all, we are going to start with the steric hindrance and how the steric hindrance is going to be related with steric inhibition of resonance and what do you call as your steric inhibition of protonation. So let us have this concept and we will interrelate all these concepts. The steric in the sense here, children, bulkiness. And next one, hindrance. It's nothing but what do you call as here interruption. So that let's go through this. By taking suitable examples, we will go through this one. First of all, children, let me show a very simplest example. We will start with that cis-butadiene. Let me start with this cis-butadiene. Let us go through this. And I'll take what you call as here trans 2 butene also. Let me take this also. And what is happening with respect to this cis and trans? See here, children, in case of this, what we are seeing here, cis is concerned. See, this methyl groups are going to be same side of the double bond plane, whereas in trans, the methyl groups are going to be opposite side of the double bond plane on the two carbons, first and second carbon here. See here, when the bulkiness of these groups are going to be more, that overlaps with each other. Hence, it's going to cause more repulsions. When it causes, what do you call as here, more repulsions? Of course, it's not at all the simple repulsions. It's due to van der Waal radii. Whenever the van der Waal radii of these both groups overlaps each other, no, then what happens means, then the repulsion occurs. That's the case. What is happening in this aspect, that's going to be cis is concerned. When repulsions are going to take place, then what is happening means it's going to, the dipole moment is not equals to zero. Why? Because the same groups are same side of the double bond plane. Whereas coming to this, children, trans isomer, when you have seen this trans, the groups are going to be far away from each other on the two carbons. Then what's almost all, the dipole moment is equals to zero. So we don't go this much of simple example for the steric hindrance, children. Just one more example, let me teach you, that's related with, let us take nitrobenzene, and that nitrobenzene is going to be, it is going to be substituted with this, what's called here, whenever it is substituted with this, nitro group is going to be substituted, what means, it's what I am taking, the nitro group is going to be substituted on this here, benzene, nitrobenzene. And this is the first case that what we have seen with respect to this. Whenever we have seen this, let us go through this, children. And second case also I am taking the nitrobenzene. That is also going to be what do you call as here, nitrobenzene. Whenever you have taken nitrobenzene, children, in both cases nitrobenzene. But here in first case, I have substituted with two bulkier groups like tertiary butyl group, tertiary butyl groups here. So then what is happening, children, here? So these two groups on ortho position of benzene, which are going to cause hindrance, what that they don't allow this benzene ring to participate with resonance with the nitro group here. So that then what is happening here means, so this nitro group goes into another plane. That's the case with respect to this. Whereas, and here this bulkiness, this is the sterically hindering, what do you call as here, this benzene, and not to allow to participate in what do you call as here, this pi electron conjugation with CN bond. So that's why immediately, due to this repulsions caused by this, van der Waals repulsions caused by this, makes to rotate in out of this plane here. This goes out of the plane here. So whenever it goes, children, out of the plane with respect to the nitro group, let us see here. But in this case, children, what's happening in this case means, let us see this case also. What is going to be happening in this case means, let us take the double bonds here in the benzene ring, right? That everybody known, Baba, here. Yeah, children, see here, this is going to be the nitro group here, which is in conjugation with pi bond of, what do you say here, pi bond of benzene, right? So this is electron withdrawing group, Baba, here. Whenever your electron withdrawing group is there, then what's going to be happening means, this withdraws the electron from benzene ring and acquires what you call as your double bond character, children. Whenever, Baba, it's going to acquire the double bond character, then what's going to be happen here means, C double bond N is formed here. It's what's going to having C double bond N. So that here there is the bulkiness causes steric hindrance. The tertiary butyl group causes what do you call as here? That's nothing but steric hindrance to this nitro, to the benzene, and making to rotate the nitro group out of the plane, and it remains as it is only. That's going to be remains as it is. This is in one plane and this is going to be in another plane. There is no question of any kind of conjugation or pi electron shift from benzene to nitro group, though it is electron withdrawing in nature. So coming to this, whenever we compare the bond lengths with respect to that, based on steric hindrance, that's known as your children, the CN bond length in this case, let us take this case as A, and CN bond length this case as B. So coming to the first structure, whatever is called here, in CN bond length is going to be, in first structure is greater than that of second structure. That's very clear. It is also due to steric hindrance, Baba, here, what we have done. Why? Because due to these bulkier groups, it makes to, what do you call as here, cause the repulsions in between nitro and bulkiest, this tertiary butyl group. It's clear, children. Then, Baba, here, this is going to out of the plane. That CN bond remains as it is. There is no question of conjugating with this. That's the case here. Regarding one more example. Okay. See, let's go to the third example, children. Let's do this third example is a bit important. It leads to what you call as our SIR and ortho effect also. Let me show you this. See, let me take this one compound that's going to be dimethyl benzene acetic acid. See, listen, this is dimethyl benzene acetic acid, and this is also what we have taken is, another one is taken as, what do you call as here, simple benzoic acid. That I have taken, what do you call as here, benzoic acid, Nana, here. So when you have taken, children, let me take this. See this? Here what is happening means, these methyl groups, when we have seen the methyl groups, are there at ortho position. So these two are located at the ortho position of benzene. And whereas coming to this, these ortho groups hindering CH2 group, not what do you call as here COOH group. They are not going to hinder this, right? After this, children, let me come to this benzoic acid. So this is going to be, these two are going to be in the same plane. This is sp2 and this is also going to be sp2, or in same plane, and undergoes what do you call as here, this pi conjugation with C bond, and due to its electron withdrawing nature, and of course it's going to show M effect also, that's going to be here, it shifts in this case, and that has been going to be shifted here, so that this is going to cause what do you call as here, resonance. Here the resonance is going to take place in this case. So when the resonance takes place, this is due to pi electrons, Nana, here. It becomes, what do you call as here? What's called here? It's rotation. I mean, going to back plane is restricted here. And then let me take this here. It's not hindered. Which is not hindered? COOH is not hindered. When these two compounds are reacted with alcohol, generally acids reacts with alcohol and undergoes esterification here, whereas this undergoes esterification very easily. And coming to this, children, I'm just going through this. There is no chance to undergo esterification because of this resonance. Whereas here, resonance is inhibited by benzene ring. It's what you call as here, resonance is inhibited by benzene ring. Not only that, this carboxylic group is away from this. It's no esterification here, none here. It's coming to this case also. This example also we have seen. When we are going for that next example, when we move to next example, let's start another example, children. With respect to this, orthopara directing group also, how this, what do you call as here, the bulkier groups directs the incoming group. Let me take this example. The benzene is substituted with tertiary butyl group. Whenever it is subjected to nitration, that's concentrated nitric acid and what do you call as here, H2SO4, 1:1 mixture of what do you call as here, concentrated and nitric acid, and this one liberates nitronium ion is the electrophile. So this incoming group, whether it is going to, it gives ortho and para substituted compounds. Well, it goes to ortho or it goes to para. What is possible? Both possibilities are there. But here, children, we should observe that due to this bulkier group, no, it inhibits the incoming electrophile. The incoming electrophile is inhibited and it restricts the incoming electrophile to ortho position to the maximum extent, but it is going to direct to the para position to the maximum extent. That's why in this case, the major product is going to be this para nitro, what do you call as here, substituted compound here is the major product, 99%. Whereas ortho is going to be very little extent, Baba, here. We can ignore this. That is also one of the application of what you know as here this. It's very, very less percentage. So that's no need of the percentages, but the maximum extent and major product is going to be this nana here. Oh, it's clear. With respect to this, what we are doing, so many examples we can do, children. Very, very simple example we will do. Let me take CH3, CHI, and also what do you call as here, CH2I. Just without catalyst, that's going to form an alkene. Why, Baba, here? Due to steric repulsions of this iodine, bulkier group, steric repulsions of bulkier group. But the same is not possible when it is disubstituted with chlorine. Then it requires what do you call as here, catalyst here. Then it's going to require catalyst zinc powder. So that is going to be needed in this case. In first case, no catalyst is required here. Followed? So it's easily eliminates without catalyst. Because of that, what do you call as here, steric hindrance, nana here. It's clear, Baba, here. Let me proceed to what do you call as, after knowing all this, we can go any number of examples. Let me go for a little about SIR in what do you call as here, benzoic acid. Let me take the benzoic acid and substituted benzoic acid also. This is benzoic acid. These two, pi, benzene ring and C double bond O is in the same plane, Baba, here. And let me go through this. Another example also I'm taking here like this. It is also going to be in the same plane or not. Let me see. Methyl I have taken. In the next step, I am going to take the third example like This we can write many examples, but not required, children. Just let me finish this. Here I am taking bulkiest group, right, children? So here the steric inhibition of resonance was going to be the inhibition of resonance. Sterically, it's going to inhibit the resonance. It's going to be maximum in case means steric inhibition of resonance is going to be increases from what do you call as here 1 to 3, right? That's called whenever it is inhibits the resonance. In this case, this goes to the another plane. Which goes to the another plane? This is going to maximum extent COOH goes to another plane, and this all remains in one plane. That's the case we have seen here. So that is it only possible whenever the groups are at ortho position. Not all the groups, children. So that like NH2, we cannot prefer that at ortho position in this case, because that's amine and this is carboxylic acid. So here, this is what's called, children, here, what we are doing here means this kind of inhibition of resonance is called, what do you call it? Whenever the substituent, bulkier substituent at ortho position, that's named as what do you call as here ortho effect. Then whenever this, due to this ortho effect, what is happening? That's what is called here. The ortho effect is going to be increases from 1 to 3. As the ortho effect increases, what's happening means acidity is also going to be increases due to what do you call as here inhibition of resonance by bulkier group, due to inhibition of what do you call as here resonance by benzene, resonance by what do you call as here benzene pi bond, benzene pi bond with what do you call as here C double bond O group. So this is, it's whatever the group may be at ortho position. If it is bulkier, no, that causes what do you call as here the resonance with the carboxylic acid group. So whenever it goes out of the plane, in this case, in third case, what's happening means, children, that's going to other plane, right? Whenever it goes to other plane, no, let me show you that also. Whenever it goes to other plane on the benzene ring, then let us see what is happening with this due to these bulkier groups. This carboxylic acid is going to be undergoes what do you call as here resonance independently, and it's going to form what do you call as here two resonating structures. That's what do you call as here it's going to give us what's known as here two resonating structures. Hence, the proton can be liberated very easily. That's going to liberate the proton very, very easily. That's happening in this case, Baba, here. So that any group at ortho position will increase the acidity of what do you known as here this one. What's called here? It's bulky group substituted benzoic acid. That's called what do you known as, in other words, SIR. Right, children? When we go to this SIR, any ortho substituted acid is going to be more acidic in nature. So by that way, that means, which is more acidic means, as the bulkier group at ortho position increases, that's going to be more acidic, like this. I am doing here. It's benzoic acid. And next is going to be methyl benzoic acid. That's because of the increase in what do you call as here size, than that of what do you call as this, what's known as here propyl benzoic acid or tertiary butyl benzoic acid. So its acidity is going to be increases due to ortho effect. So this is called what's simply in ortho effect, or it's called steric inhibition of resonance, children. One more concept, children, just I'd like to finish within no time with respect to what is SIR and what is SIP. SIR and SIP in aniline. What is the difference in between these two? Coming to this, children, first example I am doing with this. Let me show you this. What's I am doing? SIP, steric inhibition of protonation. Let me take aniline here, Baba, here. Aniline is taken. The aniline is going to be protonated in first structure. That's what you call as here positive charge H. It has no any other substituent at ortho position. Second case, Nana here, let me substitute one methyl group, and this also I'll protonate, right? Because this also I'm going to protonate with respect to this. It is substituted with what do you call as one proton and one methyl group. And also what is called here, this is what we are doing is nothing but ortho substitution is there, and this is also substituted with this one. Followed or not? Or else, see, we will do first of all what's called here, we will remove this. What is the difference in between SIR and SIP? We will see. First, I'll show you, children, SIP. Now, what I am doing. Next, I am going to protonate the same. This nitrogen is going to be protonated with methyl group without any substituents here or at ortho position. This is the nitrogen which is having tendency of donating lone pair. It's what is going to be happening means due to the increasing these groups, its tendency of protonation decreases from first, second, and third, Baba here. It's what you call as first to third. Tendency of lone pair of nitrogen. What do you call as here? Decreases what's known as here its protonating ability. Its protonating ability. Why? Because of what do you call as surrounded by what do you call as this groups. Nitrogen is surrounded by groups. Now, see, in the SIP, this is what we are saying means SIP. Let me take this example one more. In which case the SIP is going to be more. I'll take this also. Here, what is called here, in which case, just what I'm talking is same groups I'm taking. Hydrogen, hydrogen, protonated lone pair, that's what you call as. And also, this what I'm doing is with respect to this, it is nothing but substituted with two methyl groups and protonated tetrahedral. And this is also going to be nitrogen is protonated, and also it's going to be what is I'm doing here means I'm going to substitute here nothing but what is say two isopropyl groups. That's what I'm doing is what's called here two isopropyl groups. What is going to be happening? So this is what's called here two isopropyl groups. Whenever we are taking here two isopropyl groups on nitrogen. Sorry, children. This is where we are going to take two isopropyl groups. We will erase this and go for next. It's what I'm drawing here. This it's the nitrogen is going to be substituted with it's protonated. Again, I'm doing protonation, children. This is isopropyl group. This I have done with ice. Where the nitrogen is surrounded by the more bulkier group means, is it first case or second case or third case, Baba here? It's going to be the third case. So this is called SIP, steric inhibition of protonation. And let me show you another case also. SIR also I'll show you. What's the SIR? Sir, what do you mean by this SIR? Let me take this benzene with only two hydrogens in the first example, and this is substituted by two methyl groups here. It's two methyl groups. Again, what I am doing, second case, simply I am taking two examples. Just it's what I am taking is going to be, it's I am taking here, this is same two methyl groups. Here I have done, slowly I am increasing the size of the group at ortho position. When I am increasing the size of the group at ortho position, see children, cautiously you observe this. This is what I'm showing you is a clear difference in between SIP and what do you call as here SIR. The first case is called SIP. Whenever you are going to increase the size of the what do you call as here group size at ortho position, keeping this constant. These groups are kept constant on nitrogen. Here you are increasing the size of this group. Here it is called, it increases what you call as here SIR. Whenever it increases SIR, keeping this constant group, nitrogen which is going to be substituted are covered by two similar methyl groups, and whereas the ortho positions has been, we have been changed the size of this group, right children? When we have changed Nana here, say hydrogen to methyl, methyl to ethyl, and I can go any other tertiary butyl, etc. These groups which are going to hinder, what they are going to hinder, they are going to hinder the resonance with what do you call as here lone pair. This is called SIR, children. Let me go. Let me move to another last and but not least. A very simplest concept I'll teach you here. Suppose children, I'll take with this. Once I have taken one example, just I'll do with this. This I am giving X. This I am giving also X. This I am doing with Y. And this also I am doing with Y groups are substituted on nitrogen. Let me tell you very simplest logic here. So when the size of Y increases, the size of Y alkyl, let us take alkyl, Y alkyl increases, that's called what do you know as here SIP, Baba here. If you are going to increase the size of X, when the size of what do you call as here X, let us take alkyl, because just alkyl, and this is going to be what you know as here SIR. Let me do one example. I'm going to finish SIP and SIR difference here. Let me do this, children. First example I am taking with SIP is concerned. This is nitrogen is protonated. That is going to be aniline. What's called here, it's going to be aniline ion. And now what I am doing with this, straight away I am going to substitute with two methyl groups. It is also going to be two methyl groups. It's protonated, tetrahedral this. And last but not least, that is nitrogen I am substituting. The protonated amine I am writing. I don't discuss here KB, Ka and all. Later we will see when we come to the regular class. This here I'm showing what's the difference in between SIP and SIR. Here you see children, from 1 to 3, what's happening, Baba? Here SIP increases. SIP increases. Conjugate, what do you call as here? Acid. What do you call as here? Stability. Conjugate acid stability decreases due to what do you know as here? This. Due to bulkier groups. Due to what do you call as here? Bulkier groups. Why, sir? Why? Why? Because bulkier groups inhibits the incoming proton. This proton wants to enter, so that is going to be stopped by this one. So the inhibition of protonation tendency has been decreased from what do you call as this to here. So SIP is increased from what do you call as 1, 2 to 3. So that stability of this protonated amine is conjugated acid amine is going to be decreases due to bulkier groups, right? So that's called what's known as here SIP. SIP increases. What decreases, children? Let me write in this. SIP increases, basicity going to be decreases. Now, let me take this, children. And I'll take protonated amine with respect to SIR. I'm keeping this standard. I'm keeping this NME. Just wait 1 minute, children. I'll finish with these two examples. This is methyl and this is methyl because this is going to be, let me take what's called here same. This is also, it's called this, what is known as, this is also H plus. I am taking here same methyl. I kept this constant. This group constant I kept here. When I kept this group constant, nitrogen substituted group constant, but here I am increasing the bulkiness of the group. In which case, repulsions are going to be more. In the second case, this is in the second case, what is happening means what or bulkier, what do you call as here, ortho substituted group. Bulkier ortho substituted group, what do you call as here, causes greater repulsions. Whenever it causes greater repulsions, what happens now here? This goes to another plane and repulsions, hence that what do you call as here, this group nitrogen lone pair containing group goes to another plane, that goes to, hence this group goes to another plane. Hence, tendency of donating lone pair increases. Tendency of donating lone pair increases. So, means tendency of donating lone pair increases, which is more basic means, which is going to show more basicity means, second one, SIR increases, no children, that is what do you call as here, ortho effect increases, no, that is going to increase the basicity of aromatic amines. Basicity of what do you say here, children? Aromatic amines, right, children? Okay, children, this is what I'd like to finish for the sake of this introductory concept. Let me stop. Thank you very much, children.